So now we define t from C01 to C01. So Tf of t I define as integral 0 to t ffs ds. So we are taking the indefinite integral of a continuous function, it is always continuous. So t definitely maps C01 into C01 and this is a linear map. So we want to show that t is continuous and also show that norm of t power n is equal to 1 over n factorial. So let us try to do that. So mod TFT is less than or equal to, so integral 0 to 1 mod Fs ds 0 to t, sorry, and mod Fs is less than or equal to norm f infinity, and then you are left with integral 0 to t, and so you will just get t here, and that of course is less than or equal to norm f infinity because t is less than 1, and therefore this is true for all t. So norm Tf infinity is less than or equal to norm f infinity. Now if you took f to be identically 1, then you get Tf is at t is just t, and then you see that norm Tf is equal to 1, norm f is also equal to 1, and therefore you have equality, and this implies that norm t equal to 1. Now let us look at t square f at t. This is equal to integral 0 to t of TFT TFS ds. So mod t square f t is less than or equal to 0 to t mod TFS ds. But t of s we have just computed, that is less than or equal to norm infinity. I have just computed this mod TFT is less than norm infinity into t, so integral 0 to t s ds. So that is equal to t squared by 2 norm f infinity. Therefore, t square f norm of t square is less than or equal to 1/2. Again you take f equal to 1, f of t is t, f t square t, so f equal to 1, then Tf is nothing but t, and t square f will be t squared by 2, and if you take the norms you will get half on both sides, and therefore you get in fact that norm t square equal to 1/2. Now complete by induction. And that will finish. So let A be a n by n matrix. Then A defines a linear transformation, and in finite dimensions all linear transformations are continuous. So A defines a linear transformation. Let us take it from as ln1 going to ln1. Remember, ln1 is the Rn with norm 1. Okay, so that is the norm, sum of the absolute values of the coordinates. So compute norm A. Recall that norm A is nothing but So, one of the various formulas super of x not equal to 0 of norm ax 1 by norm x1. So, let us compute first axi. What is the ith coordinate of ax? This is nothing but sigma j equals 1 to n aij xj. So, mod axi is less than or equal to sigma j equals 1 to n mod aij mod xi mod xj. So, norm ax1 is sigma mod axi, and therefore that is less than or equal to sigma, this is I equals 1 to n. So, I equals 1 to n sigma j equals 1 to n mod aij mod xj. Let me interchange the order of summation. Everything is finite, non-negative, no problem. So, j equals 1 to n sigma I equals 1 to n mod aij mod xj. So, I want norm x1 to be precipitated out. So, I will write this as less than or equal to max 1 less than equal to j less than equal to n sigma I equals 1 to n mod aij. The biggest of these numbers into sigma j equals 1 to n mod xj, and this is nothing but norm x1. Consequently, you get that norm ax1 by norm x1 is less than or equal to max 1 less than equal to j less than equal to n sigma mod aij. I equals 1 to n. These are the column sums of the absolute values of the entries. So, you take the add up the elements in each column and then you take the maximum of these. So, you get this. Now, let us, I want to show in fact, so this is equal. So, this means that norm A is less than or equal to this quantity. Now, assume that max occurs at some j naught. Then you consider x equals ej naught, the vector with 1 in the j naught place and 0 elsewhere. So, norm x1 is nothing but 1. And what is ax? Ax is a of e naught, which is equal to the j naught column. That means a1 j naught, an j naught. Therefore, norm ax1 is equal to sigma mod ai j naught I equals 1 to n precisely, and therefore we have the norm is less than or equal to this and it is actually attained for the vector e naught, and therefore we have that norm a is equal to max 1 less than or equal to j less than or equal to n sigma mod ai j I equals 1 to n. So, in the same way, I would like to you to try, if A maps, if you consider it as L infinity to L infinity, then show that norm A is the max 1 less than equal to I less than equal to n sigma j equals 1 to n mod aij. So, this time you take the row sums of the absolute values of the entries of the matrix and then take the maximum. You will get the norm of A, the same matrix considered now as a linear map from Ln infinity to Ln infinity, that is Rn with the L infinity norm. Okay. Then 8th, so Mn is all n by n matrices. So we can identify this with Rn square and use its topology. Since all norm topologies are equivalent, doesn't matter what you are going to use. So I am going to identify Mn as a big vector which I string out all the rows or all the columns, and I get a n square dimensional vector, and so be it is. So GLN is invertible matrices. Show that GLN is open in Mn. This is almost immediate, there is nothing to do. You take the function which is determinant, which is from Mn to R. Then this is a continuous function because determinant is nothing but a polynomial in all the variables, and therefore it is a continuous function. And then GLN is nothing but set of all A such that determinant A is not 0. So this is the inverse image. So this is determinant inverse of R minus the origin. This is an open set, so inverse image of open set is open, and therefore GLN has to be open. And we will do a little more complicated version of this in infinite dimensions presently. For that I need to do another exercise. So 9, let V be Banach. So what is L of V? All bounded linear or continuous linear transformations V to V. LVV we said we will write as LV. So LV is also a Banach space. Okay. So let AK belong to LV, K equals 1, 2, 3, etc. It is a sequence. So we want to give a meaning to S equals sigma AK. What do you mean by a infinite series? So if you have finite sum, we know what we mean, we just do it pointwise. So what do we mean by this? We do it exactly like we do in real numbers. So you take SK, SL is equal to sigma K equals 1 to L AK. This is a sequence of partial sums. So if SL is a convergent sequence in LV, we say that the series converges and the limit of SL is the sum of the series. So exercise is, assume sigma K equals 1 to infinity, norm AK is convergent. Then sigma AK is convergent. This is just as in real numbers, absolutely convergent series are convergent the same way. So let us take SL to be sigma K equals 1 to L AK. So SM equals sigma K equals 1 to M AK. So you have that, so let us assume M is bigger than L. So SM minus SL is equal to K equals L plus 1 to M AK, and therefore norm of Sm minus Sl is less than or equal to sigma K equals L plus 1 to M norm AK. But sigma norm AK is a convergent series, so this is a, by the Cauchy criterion of convergent series, this can be made less than epsilon for all NL, ML large enough, and consequently SM, so this implies that SL is Cauchy, V is Banach implies LV is also Banach, and therefore SL converges to some S, and that is called the sum of the convergent series. So every series. So next exercise which will use this, let V be Banach and let norm A be less than 1, A in LV. Then A is invertible and I minus A, sorry, A is not invertible, sorry, excuse me. I minus A is invertible, I is the identity, and I minus A inverse is sigma I plus sigma K equals 1 to infinity A power K. So this is like if mod x is less than 1, then 1 by 1 minus x equals 1 plus x square and so on. So this is the infinite dimensional operator version of that. Okay, so in LV, if T1 and T2 are in LV, then you can compose the two, T1 T2 or T2 T1, doesn't matter. So T1 T2x is T1 of T2x composition. Therefore norm of T1 T2x is less than or equal to norm T1 times norm of T2x, and this is less than or equal to norm T1 times norm T2 times norm x. Therefore norm of T1 T2 is also in LV, and norm of T1 T2 is less than or equal to norm T1 and norm T2. So norm of A power K is nothing less than or equal to norm of A power K. Therefore sigma norm of A power K is nothing but less than or equal to sigma norm A power K. Norm A is less than 1, and therefore this is a summable geometric series, and therefore this is convergent, and therefore sigma A power K is convergent by the previous exercise. So now you look at I plus A power n into I minus A. If you expand this out, this will turn out to be I minus A to the n plus 1, and this will also be equal to I minus A into I plus A power n. So if you take the sum of the series, if you take n tend to infinity, so you get S times I minus A equal to identity equals I minus A times S. So therefore I minus A is invertible, and its inverse is given by S, which is the limit of this partial sums, which is I plus sigma K equals 1 to infinity A power K, and therefore you get Okay. Okay, so now V Banach and G is invertible operators, mappings, linear operators, transformations, whatever, in LV. Show that G is open. So this is the infinite dimensional version of the matrix problem which we saw earlier. In case of matrices which are in L of Rn, we saw that just the determinant helped us. The determinant not equal to 0 are the invertible elements, and therefore we immediately got that it is open. So now we want to show that G is in fact open, and we do not have the notion of a determinant. So let us take A in G, and you take B such that norm B is strictly less than 1 by norm A inverse. Then let us look at A minus B. This can be written as A times identity minus A inverse B. Now what about norm of A inverse B? This is less than or equal to norm A inverse times norm B, and norm B is less than 1 by norm A inverse, so this is strictly less than 1. So this is invertible, this is also given to be invertible, and therefore A minus B is invertible. So this implies that the ball center A and radius 1 over norm A inverse, the open ball. So this is set of all B such that norm of B minus A is less than 1 by norm A inverse is contained in G. Therefore, G contains the open ball in every element inside it. This implies that G is open. Okay. So the last exercise which I want to discuss with you is the dual of a product space. So let us take V and W norm linear spaces. Then we consider the Cartesian product V cross W, and on it I am going to put two norms, one xy, I am going to take as norm x, this in V, plus norm y in W, or max norm x V norm y W. This, like in the case of C1, we had two possibilities for the norms, so we can do this here also. Then both these define norms on V cross W. So on any product space you can at least have these two. You can have many more, and so show that V cross W with the norm dual of that is nothing but V star cross W star. And what is the norm? The max of norm V star norm W star. So V cross W star is also product space. It has possibility of two types of norms, one from V star plus the norm of W star, the other time with the maximum of these two. I claim that the dual of the space is precisely this. Okay, so let us take F comma G in V cross star W star. Define phi of xy as fx plus dy, xy in V cross W. So this is a linear functional, and what is mod phi of xy? This is less than or equal to norm f norm xv plus norm g norm y w, and that is less than or equal to max norm f. So this will be in V star, this in W star, V star norm g in W star into norm xv plus norm y, and therefore norm phi is less than or equal to max norm f V star norm g W star. Now we want to show, now let phi belong to V cross W star. Any element in the dual, define f to be f of x equals phi of x0, and define g of y to be phi of 0y. So xy is x0 plus 0y, and therefore phi of xy by linearity is nothing but fx plus gy. And what about mod fx? This is less than or equal to norm phi times norm x in V, and mod g of x y is also less than or equal to norm phi into norm y. So this is mod fx. This means f is in V star, and this also means g is in W star. Therefore fg will belong to V star cross W star. And what about the max of norm f norm g? This is still less than or equal to phi. So previously we showed norm phi is less than max norm f norm g. Now we are showing that every phi can be thought of in the same way as an fg, and max norm f norm g is less than or equal to norm phi. So this means that V cross W dual can be identified as V star cross W star, and if the norm here is norm x norm V plus norm W, here the norm will be max norm V star norm W star, because we have that. Therefore, since the two inequalities imply that norm phi is equal to max norm f V star norm g W star. So as an exercise, if norm on V cross W is max norm V norm W, show that V cross W star equals V star cross W star with the norm V star plus norm W star. So one can try to do this yourself. Okay, so I think we'll wind up with this.